Yay. All right, so today, really, what I want to chit-chat about is every stat textbook is kind of set up the same way. The beginning of it, and it's usually right before the section on central tendency, has a bunch of stuff. It's got everything from graphical displays of information, all kinds, bivariate, univariate, multivariate. It's got types of data, it's got z-scores, it's got all these things, the prerequisite ideas that I mentioned that's going to be in the quiz for next week. And it's all kind of combined into one place, and they all kind of imply the same thing. Learn all this right now, because we're going to use it in like 7 weeks. And I don't see the point of that, because you won't remember it past next week if we do that. So what I've kind of done is I've kind of gone into the first part of your textbook before central tendency and realized what we're going to be using immediately. And I've kind of developed this around that. So this section, Intro to Prob and Stat, really isn't in your book, but it is in your book. It's pieces of your book. I've kind of extracted the things that we're going to be using immediately. The other stuff is important too, but it will be important later on. For example, a z-score. Z-scores are awesome. They're awesome. But it makes a lot more sense to talk about them right before we talk about the normal distribution. That's where they make the most sense. Percentile ranks, ogives, for example, are awesome too, especially if you have a child and you take your children to the pediatrician. Understand those charts they give you. Totally awesome too. But it doesn't make sense to talk about ogives until you talk about relative position. So I've kind of extracted all that stuff out and diluted this down to a couple ideas that we'll kind of look at in depth, if that's okay with you guys. It seems to work pretty well. So let's get it started. The big one, this course is all about data. It's all about data. And I didn't know how to define that, so I took a stab at it there. It's something you're interested in. Something that you're interested in. Is this going to work with the... It's an E. So, I think this is going to work. So anyway, and I'll post this PowerPoint, so don't feel the need, unless you want to. You don't have to like scratch notes then if you don't want to. You'll have this entire thing available to you later on today. So keep that in mind. Everything I show you, minus the stuff on the board, but I'll try to record that as well. It'll be available to you within 24 hours. So anyway, so we're interested in data. That's kind of what makes this course go round, is dealing with that. Dealing with how to crunch. I often call it crunching data. Getting the data and doing something with it, whether it's just reporting it, whether it's analyzing it, whether it's predicting off of it, all kinds of things we can do with that. And 243 and 244 as well, the second course. The two kinds that we kind of have broken it into are qualitative, also called attribute. And this happens, that you deal with this on a daily basis. I call it non-numerical. So for example, if I was trying to keep track of the types of cars in the parking lot. That's non-numerical data, because you label them as Ford. Hi. Ford, come on in. So, are you looking for, let's make sure, is stat class 243?
Yes.
You're in the right place. Right? We dealt with the history thing last time, so we're good. We're gold. What was I saying? Non-numerical, right? Non-numerical data. Which method of payment? Visa, MasterCard, Discover, that kind of thing. So not something that isn't dealing with numbers. Be aware, and this is I'll mention this over and over again as the course goes on. Many things that are non-numerical are disguised as numbers sometimes. For example, when you guys do student evaluations for these classes, I don't know if you've done them yet or not. Well, not for this class, but for last term and the term before. If you look at they're called Likert scale questions. How would you rate your answer to the following question on a scale of 1 to 7? 1 being strongly disagree, 7 being strongly agree, 4 being neutral. Well, there are numbers there, but those numbers aren't really numbers. 1, it means strongly disagree. That's a non-numerical data point. 7 means strongly agree. That's a non-numerical data point. And that's an issue with Likert data. But it's used, and it's useful. You gotta be careful what you do with it though. And we'll talk more about this in this class and also in 244 about how to deal with qualitative data the proper way. So anyway, that's qualitative. There's not a whole lot you can do with it, honestly. Talking about species of fish in a certain pond, you're studying the effects of fertilizer running into the Crooked River. What effect is it having on the wildlife in there? Okay, so you got non-numerical, rainbow trout, steelhead, those little tiny fish my son catches by hand with little spines on them, whatever the hell they are. I don't know what those are. Anyway, non-numerical. Now, If you're talking about, for example, the size of those fish, so you pull the steelhead out, and you might be talking to people and say, man, the steelhead used to be bigger in this creek. Yeah, I used to get them out when they were this, not like fishing tail. But they used to be bigger. They seem smaller now. So you're talking about the weight of a fish, or the number of fish you've caught out of a lake. That's not non-numerical. So if it's not, that makes it numerical, double negative. So that becomes numerical data. So we're going to call that quantitative. We're going to call that quantitative. And this is kind of our favorite, at least in this class, because that actually gives us something to do. Oh, I shouldn't say that. You can do lots with qualitative data too. You can just do a lot more when it's quantitative. You can do a lot more with it. And I've split it into two categories here. Discrete versus continuous. Discrete versus continuous. So an example of a discrete data point or a discrete data value would be the number of steelhead caught beneath, I don't know, where does steelhead run? Benham Falls? Are there steelhead in the Deschutes? Let's say there are. Let's pretend there are for the sake of argument. Number of steelhead caught under Benham Falls, blah, from May to October. Continuous would be the average weight of those steelhead, or the weight of each one of the steelhead. Because you measure weight. You measure weight, but you count a number of fish. And I like both of these because depending on what kind of data you have, it makes you deal with them in different ways. Very often, the data you guys experience in the media and news outlets is discrete in nature. I just saw a Gallup poll that said the majority, I think I may have mentioned this to you in class, I know I posted it on the Stat of the Day blog yesterday. The majority of Americans are now opposed to the war in Iraq, or the operation, it's called a war, the operation that happened starting in 2003. That's a response from discrete data, because they took a sample, well, more on samples later. They took a sample and they asked a bunch of people in the sample, yay or nay, do you think it was a good idea or a bad idea? And of that sample, more than half said it was a bad idea. So they had to count that, more than half of them. So if there were 1,000, maybe 550 said no, it was a bad idea. So you count that. That person says no, that person says no, 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 yes, no, 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 yes. That's counting. That's counting. If for some reason I needed to know their ages, the ages of these people, which would be interesting, wouldn't it? It would be an interesting study to see if there was an age interdependence with their response. Do more young people say no, it was a bad idea than older people? Yeah, that would be a continuous data point. I know it seems weird, but age is continuous. Age is continuous because it's a measure of what? It's a measure of time. And time, well, I just gave you the answer. It's a measure by saying measure. So if Amy hadn't just broken the clock, even though I broke the clock, but there was a second hit on that. There was a second hit on that clock that was sweeping through. It gives you a nice visual of the continuum of time. So time is measured, although we often think of it in discrete increments, like a second going by. But there's lots of time in between those seconds. Milliseconds, half seconds, quarter seconds, and things like that. So, as far as I can tell, there are four main things that are continuous, four main data types. Time is one. Can you think of another one that's measured? Please.
Length.
Length, awesome, Jordan. Length is definitely measured. Length. Your height, even though we round our heights off usually to the nearest inch or something like that, length is definitely. Go ahead, my friend.
Weight.
Weight, absolutely. Weight, when you weigh something.
Miles.
Miles would be, I would loop that into length as well. But yes, definitely miles. Tell me your name again one more time. Robin, thank you.
Did you say weight?
Weight, yep, we got weight, we got length, we talked about time. Go ahead, Jordan.
Temperature.
And temperature. These are the four things that I've seen measured over and over again. Now, there are other ones, like miles, for example, but also volume. Like talking about a volume, like how much water is in my Nalgene over there. But volume really is a measure of cubic length.
Yeah.
It's a length, a width, and a height. So, I mean, essentially it can be decomposed down to length.
So these guys are discrete.
Those are continuous. So these are continuous. These are things that are measured. Yeah, discrete things are just counted. 1, 2, 3, 4, 5.
Yeah, that's what I thought.
Yeah, and discrete data is very, very natural to us. I mean, it's the stuff my son likes to do. Let's count stairs in Spanish. I love doing that. You know, jumping out of the pool. Oh, dos, tres. He has to teach me because I can't pass like 8. But it's very natural for discrete for discrete data. Continuous is not as natural because you have to have precision of whatever you're using to measure, and that gets tricky. I hear about CFS, cubic feet per second of water going past a certain point in a river. Okay, measuring that can be tricky Measuring length can be tricky. Measuring weight can be tricky. Max measured himself on the scale last night at the pool. How much do I weigh? He jumped up and he's trying to mess with the scale. I weigh 222. I'm like, no, you don't, buddy. That goes over there and it's got a balance. But then it gets tricky. Explaining it to a 5.5-year-old or anybody else, like, what's balanced? How balanced is balanced enough? And that's why you very rarely see these in mass media, because the level of precision you need to actually report on them correctly is usually outside of the scope and budget of most folks. You see it very often in scientific journals, and you will continue to see it in scientific journals. But Gallup polls, Quinnipiac polls, Rasmussen polls, it's all discrete. It's all discrete. It's a sample drawn and a certain number of that sample. So 1, 2, 3, 4. Cool? And we'll mix it up. We'll mix it up. And I'll keep asking you guys as we encounter data what kind it is, just to give you a feel for it. Okay? Cool so far. Any questions you guys have? Throw them out if you have.
Do you have a pencil I can borrow?
A pen? That's a good question.
Thank you.
Other questions? I got a half-eaten pear. I got a rag. Lady, yeah.
Can the data be both discrete and continuous?
That's a fantastic question, which I have no answer for because I can't think of one. The question is, can it be both? I don't think so, but that's just because I can't think of an example of it. Another question is there a fifth type besides temperature, length, weight, and time? And I only say no because I can't think of a fifth. So I want to leave it as I can't think of a counterexample. So until I can, kind of leave it at that. So I just don't see how you can measure something and count it at the same time, because by definition a measure involves a sliding scale. Unless your measurement increment somehow jumped. Discrete jumps, if you will, 1 to 2 to 3 to 4. And continuous allows you to slide from 1 to 2 to 3 to 4 between them. So I don't see how you can do both. If you can do this, you technically can't call it that. That's the best answer I can give you. Unfortunately, there's some gray in that answer too, but there's plenty of gray in this class. All right, 243 is all about this. Well, not this map. This map is a cool indication of this. But what we have here is what this class predominantly is about, which is describing data once you've collected it in some way. And I just love this map and a couple that follow because of how the data is presented. So what you're looking at here are just the results of the two main parties that ran in the 2012 presidential election. What kind of data do you think is being represented up here, friends? What kind of data do you think is being presented?
Discrete.
Tell me why, Robin.
Because you're counting votes.
Good, very nice. Robin says discrete because we're counting votes. Absolutely. They give you percentages. They give you percentages, but that's just percent of the total. And the way you get those numbers, it's something over something, and they're counted. We're not talking about the average age of these people, or the average weight, or some qualitative measure like race or gender. We're talking about who they voted for in these two categories. And what's interesting is if you add up the Barack Obama and Mitt Romney, it doesn't sum to 100%, which makes sense, right? Part of the problem, at least my opinion, with our political system is there are only two real parties. But that's lame. There should be way more, and the way more are the other whatever 1.4 or 1.6% that's not represented there. So, but the electoral college is split between them. So you got like a 2-to-1, 60-40 split in the electoral college. So what you're seeing, and what's interesting about this map, have any of you seen this map before? Or one like it? What's interesting about this is Obama won, right? Obama won. Does that map make it look like he did? And that's one criticism this map often gets is Obama won, but there's not a whole lot of blue. There's more red, if you will, than blue. Why is that? Why is that? Tell me your name.
AJ?
AJ, thank you.
Because there's higher populations in the states that are blue.
Democrats tend to win the larger population-dense areas. So an interesting thing to do is to, distort the map in such a way where you actually have the states weighted by population. So then Wyoming, for example, when you go back here, Wyoming's one of those big rectangle states. That's Wyoming right there, right? Big rectangle state. Delaware, state I'm from, right there, little tiny blue triangle state, the diamond state, the first state, home of tax-free shopping. But then when you weight it by population, there's my state of Delaware, and where's Wyoming? And you see, it's very interesting when you think about how many people, Wyoming, I believe, correct me if I'm wrong, I think it's the least population-dense state in the country. I think it's even less dense than Alaska, I think. I think. I've seen the rankings before, and I'm going by memory.
It's 500,000.
It's 500,000 people total, 500,000 in the whole state. Unbelievable, unbelievable. So this is kind of a, and this one, if you look at this map, and this has got a name, and I can't remember what they're called. This map is a projection of some kind. I forget what it's named after the guy or girl that first developed it. Now you can say, oh yeah, I see how Obama won. I see, because by people, by counts, they're now indicative. I mean, there's New York, Pennsylvania, California. Texas is smaller than it appeared on the original map, just because, again, of the density in the urban areas. Florida looks huge. Here's another neat look at it. This is back to the normal projection of the U.S., but this is now by county. So this is each state split into counties. So Delaware, again, only because I know Delaware has 3 counties, Newcastle, Kent, and Sussex. Newcastle and Kent went blue, Sussex went red. Sussex is actually the Mason-Dixon line ran either right next to or right through Delaware back in the day. And it's interesting that those undertones of North and South still exist in even that little tiny state of Delaware.
Sean, excuse me, did you study there?
In Delaware, yeah, I did.
Because that's what I did.
Oh, you did too?
In New York, yes.
Excellent, yeah, that's where I was. That's where I was. New York, Delaware, right there where it's blue.
That's how you know it.
Well, because I'm from there. But then you got Pennsylvania again. Pennsylvania's right here, mostly red. But if you remember, Pennsylvania was blue. Well, that's because the areas that are high urban areas, Pittsburgh and Philadelphia, went blue, and that's where the majority of your population is. So the folks that developed the original map, the projection that showed the population density, here are the county densities blown out. Here are the county densities blown out, which is very, very cool. So LA, I'm guessing, is that. Philly is, I think, that. There's Delaware. Where's Wyoming? Wyoming's gone now. Looks like looks like that. And I believe, if I have one more, yes, this is the same counties, but now what they've done is a gradient. So it's not only, it's more blue if they voted more Democrat than Republican, but they give it a shade of purple to show you a gradient. Like, it's not a 1 or 0, there's now a sliding, if you will, between. And I think they did.
Look at California.
Yes.
That makes sense.
Exactly, wow. Past the point, this gets ridiculous. Because now you can say, yeah, it's mostly blue, so Obama won. But I think we also had that back here. I think we had that back here as well. So past the point, it does get a little bit ludicrous when you talk about this. But this is what happened. This is what happened. This is descriptive, right? This is exactly what happened. I mean, this happened in November. If we tried to take what happened in November and extend it to what's going to happen in 2016, it's no longer descriptive. That becomes a different animal. That becomes inferential. Inferential. And we talk about this a smidge in 243, but it's mostly a 244 topic. That doesn't mean I don't want to talk about it in 243, because I know some of you are not taking 244. And I would feel remiss letting you out of this class without understanding at least what a margin of error is and how to interpret a margin of error. It's very, very important. It's very, very important. We'll analyze it in great depth in 244, but I'd like to at least pay a good service to the idea of a margin of error in 243. So rather than trying to define some of these terms, we're going to kind of play with it in context. So the idea of inferential stat is not that you report on what the data you collected was and then stop. The idea is you collect data, which we call a sample, and it should be a random sample, or as close to a random sample as it can be. I want to talk about that more in about 10 minutes, because that is nowhere near as easy as it sounds. We talked briefly yesterday about how hard it is to be random, and how hard it is to identify randomness. Briefly, very briefly. I want to bring that back. It becomes even less obvious when you look at news sources. So you take a random sample from what's called a population. So the population is who you're interested in studying. But you very often can't get the entire population. You can't ask, for example, if you're interested to find out the results of an election, they very often do exit polls. So they ask every 10th person, every 20th person exiting a poll. Why do they ask every 20th? Because who wants to ask everyone, right? You don't have the resources or the time to do it. And even if you could do it, you probably do it wrong, or wrongly. Wrongly? Yes, wrongly. So yes, you develop what's called a random sample. And exit polls are not necessarily random samples. More on that in 244. But, so you draw this idea of a random sample from your population that you're interested in. So here, check this one out here. Hopefully you can read it with that camera stuck in the middle of it. But a study claims caffeine addicts get no jolt from morning coffee. It's patently false, by the way. Works for me every day. Go ahead, take a look, see what you can see there. Hopefully you can read it. I know the font's tiny small. Sorry, guys. And I'm not so much interested in this fist fight that's happening up here, but I'm interested in what I circled in red down here. The scientists studied 379 adults who gave up caffeine for 16 hours. Okay? Okay. So, what's our population? Who are we interested in talking about in this article? Which kind of adults? I think we can refine it down even more than that. Caffeine addicts. In particular, coffee drinkers, I'm assuming. They're calling them caffeine addicts, but I think what they mean is coffee drinkers, I think. Because they're talking about, it says gave up caffeine for 16 hours, but I'm sure, if it was an American study, well, it's a British study, isn't it? It's a British study. That could be tea. Could be tea, and crumpets, and Queen Mum. But I'm going to assume it's coffee drinkers. Caffeine addicts. That's our population. So you can see why you couldn't survey the entire population. If you did survey the entire population, you know what that's called? It happens in the United States every 10 years. Trev, it's called a census. Yes, it's called a census. It happens every 10 years. And I think, I could be wrong about this, but I think the Census Bureau has finally woken up to the fact that that's dumb. And they should be doing random samples, I think. I think the census was put into the Constitution back when there were like 22 people living in the country. And you can go out to your neighbors and be like, okay, this is the entire United States, right? Sweet. So I think we're starting to realize with 310 million Americans, it's more trouble than it's worth. Anyway, so our population is caffeine addicts. What's our sample? These kids right here. That's our sample. And I noticed a couple of you kind of chuckled. We said 379 because you thought what? You thought what? This is Jen, correct?
Yeah.
Because it's not.
There's not a lot of
people in there, right? I mean, how many caffeine addicts do you think there are in the world?
millions.
Maybe a billion? Maybe a billion? I'm not exactly sure of how. Well, I'm thinking of large populations like China and India. We're not a very large population center, but I'm guessing most of us are addicted to caffeine in some way. So we'll say Chinese drink a lot of tea. We'll call that, and it's green tea, which is caffeinated. I'm not saying it's caffeine addicts. Well, it doesn't have to be caffeinated. It can be caffeinated. Indian culture, I'm not sure if tea exists in that or coffee exists in that. Let's just say there's a lot of them. Let's call it a billion. Let's say it's a billion.
In Russia, we have both tea and coffee.
There we go.
Addicted.
There's like 28 Russians though, right? It's cold there. It's cold in Atlanta. So let's just say it's like a billion people. How can 379 possibly be enough to stand for? And the answer is, it's plenty. It's absolutely enough. I know, Jen, it doesn't make any sense, does it? It doesn't make any sense. I encourage you, if you don't think, never question the sample size in this class. Rest your minds. It's a 244 argument. It really is. To decide how big a sample should be is really a 244 argument. So trust me in this class. If you still haven't had enough by the end, take 244, and we'll dispel all those worries. 379 is actually plenty. You can do good statistics with far less, even 38. Sometimes you can't get enough data points. Sometimes you start a study and people disappear during it, and you end up with like 28 data points. You're like, crap, what do I do now? Well, you can do meaningful statistics. You have to accept larger margins of error, but you can still do meaningful statistics. So anyway, there's your sample. There's your population. Caffeine addicts, your population. 379 adults, your sample. The trick is, was it done randomly? I don't know. The scientists studied 379 adults who gave up caffeine for 16 hours according to Reuters. Reuters is, you can follow the link out to Reuters if you want. But the trick is, how did they get those folks? I don't know. What I like to do whenever possible is to backtrack how the study was done. Very often a Gallup poll, which we'll look at here momentarily, in Gallup polls they'll describe to the sampling methodology used, and they'll say we use random digit calling to get our responses. Random digits mean they basically create an area code, and a local code, and then randomly generate the last 4, or maybe even the full 7 digits. So that's pseudo-random. You're assuming a person has a phone, though. So basically, when you see the word random sample, what you want to think is, did every single member of the population have the same chance of being selected? That's the question you have to ask yourself. That's what a random sample truly means. Did every single member of the population, in this case caffeine addicts, did every single member of that population have the same chance of being selected? Now, the answer to that is almost always no. Because chances are, me, as I'm going to call myself, well, actually, you have to define what a caffeine addict is, for that matter, right? You have to define what makes a caffeine addict a caffeine addict. Let's say I am one. I don't think I am, but let's say I am one. Guaranteed, if this study was done in Britain, I wouldn't have a snowball's chance in hell of being selected for it. So it's not truly random, because I'm not in there. Any caffeine addicts in here? I doubt you guys would have been selected either for this study, being as it happened in Britain, right? But the question is, can we live with that lack of randomness to that extent? And that is an answer that we will develop over the course of 10 or maybe 20 weeks together as we go through our stat courses. You should know that right now, because it's almost a case-by-case, very, very gray area basis. Cool? But the big thing is just being able to identify the population they're interested in and the sample they use to get it. That's really the big idea. Looks like you just got it. All right, cool. So what you want to know about that population is called a parameter. But why is this class called probability and statistics? It's because statistics are what you get from your sample. You don't get the parameter. Almost never. I should say, I want to caveat that with almost never. Because in order to get a parameter, you have to know the entire population, which is patently absurd, really. Now, it doesn't have to be. For example, I'll very often talk about you guys as a population, like when I collect all your exam grades together, and I report on your average, your class average. I'll often call that the parameter because you are the population I'm interested in. That's totally cool. That's totally cool. But in general, these studies that are done inferentially are from sample results applied to the population. And more on that as we talk about the Gallup Poll I'll have up here in a couple minutes. So we usually get statistics in the hopes that those statistics are properly approximating the parameters. We do want these. We want parameters. We want them. I want to know how much the average heart rate changes for a caffeine addict who doesn't get their morning jolt or their morning cup of coffee. I want to know that. I want to know, is it 12 BPM change? Is it 13 BPM, 14 BPM? I want to know if their body temperature changes a meaningful amount. I want to know if they blink more than the caffeine drinkers that get their coffee. I want to know if they sweat more or if they twitch more. I want to know all these things, but you're never going to know it. What you're going to know is you're going to know the statistics that come from your samples. And then you have to adjust those to talk about your population. We'll see an example here in a minute. Is that fair so far? You guys buying that? Ish. Get used to the word ish too, because this class is full of that. You're about to see your first ish here in a minute. This is a Gallup poll from. It's also what? It is, because it applies to everything, Jordan. It applies to everything, ish. I mean, it's a wonderful thing. So here, you'll see your first ish here. Okay. So this is from a couple Marches ago. I can't believe it's 2 years ago now. It's amazing. There's the headline. U.S. oil drilling gains favor with Americans. Go ahead, friends, take a look. Take a look. Take this all in. Take this all in. Take a look-see there. See what you can see. How many of you guys have looked at Gallup polls before online, or Rasmussen polls, Pareto poll, some kind of poll somewhere? I encourage you guys, if you're ever reading a news article, do you hear smoking isn't bad for you? Go find the article that your friend sent you on Facebook and follow the links to eventually get to the study that said nothing like that, but somehow got transposed into smoking isn't bad for you. So, Jordan, go, my friend.
Yeah.
You sure?
Yeah.
Okay. So this is kind of a diluted version of what this entire article had in it. I cut and pasted the tables and the titles. I left out quite a bit. I put the sampling methodology down here, though. This is important. I want to focus on that later. So there are really two kind of things I want to talk about. This one and this one. This one is the American support for U.S. offshore drilling. It says, the title, 6 in 10 Americans favor increasing offshore drilling for oil and gas in U.S. coastal areas, up from 50% in May of 2010. Okay, so their claim is that 60% of Americans favor offshore drilling. All right, that's not exactly right. That's not exactly right. But you might say, wait a minute, it has to be right. It's Gallup. Gallup doesn't screw these things up. And I'm not saying Gallup screwed up. I said it's not exactly right. 6 in 10 people definitely favor increasing offshore drilling. But 6 in 10 of which people? The ones that Gallup interviewed. Not all Americans. What are all Americans? That's the what that Gallup is interested in. That good. We're going for the parameter, Chris, because it's measuring the entire population. No, you got it. Chris, I told you, Chris. Jordan. We're going for the parameter because we want to know what the entire population thinks. But when they say 6 in 10 Americans favor increasing, I sit back and I go, wait a minute, time out. Did you ask every single American? And 6 of those 10 said they favor it? No, they didn't. Who did they ask? Did you see at the bottom there, friends? You have to look. Gallup puts this at the very bottom of their articles, and it's often very, very far down, quite a bit of scrolling. But it's down there, as it should be, and Gallup is very good for doing this. They asked 1,021 adults. And don't worry, Jen, don't worry, it's big enough. I know you're very concerned. It's good that you're concerned about that. 1,021 is fine. Tell me your name first. Jennifer, thank you.
Wouldn't it not, even if the sample size is big enough, they're not asking every single person because it's just continental.
Absolutely. It's interesting they left Alaska out and then asked about Anwar. Isn't that interesting? Good. You jumped to what I was going to have you do at the end, which is check the bias on the sample. Very nice, Jennifer. Very nice. Jen, go ahead.
Well, I was going to comment on that too, but I mean, because they don't include Alaska, but don't the majority of Alaskans agree with?
I do. Well, yes, but then again, when you look at the population density of Alaska, it might not sway the poll all that much, which is what I would counter. I love the point, and it's very important, I think, because we're talking about Anwar, we're talking about a state with a huge coast and lots of oil reserves. But then again, even if they were to include Alaskans in the poll, I wonder if it would even have moved the numbers all that much. I wonder this, because if it was truly done randomly, they call it a random sample, random digit dialing, assuming that's the case with 1,000 people, what percentage of Americans live in Alaska and Hawaii? I mean, it's not like leaving out LA or leaving out LA in New York City and then doing a random sample. I would be surprised if it changed it measurably. But nice catch. That's what I want you guys to start catching is stuff like that when you read news articles. Become critical of that kind of stuff. Excellent, excellent. So, 6 in 10 Americans are their adults, aged 18 plus, living in the continental U.S. You can just call them Americans if you want to, but more specifically, it's adult Americans living in the continental U.S. So when they say 6 in 10 Americans favor increasing offshore drilling, they don't mean 6 in 10 Americans overall. They mean 6 in 10 Americans in that sample of 1,021 adults. Now there's a problem there, because if they asked 1,021 adults again, different random samples, do you think it would come up to be exactly 60 again? Probably not. Would it come up close? I would think it would be, unless this was a goofy outlier data set. More on that later too. And if we asked 1,021 others, it'd be slightly different again. So the problem with that is, if they do it again, they have to say then 61 in 100? Or 58 in 100? Do they have to adjust it for that? No. There's a measure that allows the adjustment based off in the very, very beginning, and it's called a, here it is, margin of error. It's a very, very important number to note on these types of surveys, because the margin of error tells you how, if you will, off their statistic reported could be. Yes, they're saying it's 60%, but it could be off as much as 4% in either direction. This 95% confidence bit is a bit at 244-ish, so don't sweat that right now. We'll do that with that 244, but definitely sweat the margin of error. So that 60% might be as low as 56% or as high as 64%. So that's why I said if they ran the sample again, it probably wouldn't go up to exactly 60. It might be 61 or 62. But that's within a margin of error of this study, which essentially means it's the same results. 62% and 60% with a margin of error of 4% is what's called a statistical dead heat. You may have heard that term before in presidential elections. Romney and Obama, statistical dead heat, because Obama's at 49 and Romney's at 47, and the margin of error is 3%. And that's because you don't know that Obama's actually above by 2%. He could actually be below. But because you don't know, we're going to call it even, if you will. Is that fair? But even adjusting with the margin of error, do you believe the claim that more favor than oppose? Do you believe the claim that more favor? Now, I know it's a little incorrect to say it's American support. So let's adjust it by slapping a margin of error on there. So instead of saying that 6 in 10 Americans favor increasing offshore drilling, we'll say it better. Between 56% and 64% of Americans favor offshore drilling, favor increased offshore drilling. That's a correct statement. I'm 95% confident of it. Okay? So adjusting for margins of error, do you believe that a higher percentage favors than opposes? What do you think? When we adjust for margins of error, I feel good about that claim. Why do I feel good about that claim? Jordan, tell me.
Because the favor, even with the margin of error, is still higher than the oppose.
Good. Even at the lowest, if you take 60% minus 4 to get 56%, that's still higher than 37 plus 4, which is 41%. There's still a minimum difference of a certain number of percentage points there. So yeah, I'm okay with this claim. Am I okay with this claim? American support for oil exploration in ANWR. The question is, do you think the ANWR in Alaska should or should not be opened up for oil exploration? Notice, support for offshore drilling and oil exploration in Alaska reached new highs, which is implying that not only are they favoring more drilling, they're also favoring drilling in ANWR. Do I agree with that statement based on those numbers?
No,
Tell me your name, my friend.
Jada,
Jada, tell me why you say no. Tell me why you don't agree.
because with the margin of error, it could go either way.
Yes. So this, yes, 49 is higher than 45. So in their sample, more people said yeah than no. But that 49, yes, is really, could be as low as what? Right, 45%, all the way up to 53%? By the way, I suck at arithmetic. Check me on this. Every time I add or subtract, multiply or divide, check me on this. I can ish pretty good, but I can't add so low. No is 45%, but it could be as low as 41%, up to 49%. So if you want to think about that on a single number line, right, where 50% is right here, this one here, 45 to 53, is ish here. 41 to 49, would be ish here. So here's yes, here's no. And the problem with that, obviously, is that they overlap each other completely. Not completely, but a very large percentage of overlap. And that true parameter that you're looking for, which is the actual support of Americans for drilling it in more, is somewhere in that bar. But you're not sure where it is. It's easy to say it's in the middle, but that's a cop-out, because that means your sample perfectly represented the population, which is crap. That's like living in sin. You can't do that kind of stuff. All right? It's somewhere in here, which means no could actually be higher than yes. And that's a bit of an issue we have to deal with. And that's exactly what the margin of error does, is deal with that issue. Is that cool? Always pay attention to those margins of error and go find them. If they don't tell you where they are, you go find them. Because sometimes you have to dig for them. Sometimes you got to dig. Right now, you're getting that glazed look. Let me pause this bad boy. 39 minutes, that's not bad. That's great. So, that's a brief introduction, if you will, to the kinds of data. And there's much more to come, but we can deal with like random sampling styles in 244 when it's more important and things like that. What I want to focus on right now is, once you've got it, how to kind of get it out there so folks can process it. So here's some fictitious data. We'll actually generate some real data here momentarily from your guys' responses, which will be fun. I'm glad we have more than 10 people or so. Well, we got like 15, but we've got more than 4 because we can actually get some good data for later on. But here's some data for us to play with. 20. This is fictitious, just to make it up to prove a point. I generated some random numbers using Excel. So you've got these blocks here, and then over here that's a 17 and an 18 that you can't really see. Oops, I just knocked it off center. So So here's, I call this raw data. Data that's just, boom, presented to you like this. So we're interested in how many products are produced by each of 20 employees in 1 week. Here's the raw data. So one employee made 18, one made 29, one made 28, and so forth, and so on, and so forth, and so on. So that's fantastic. That's raw data. Give me one reason why raw data is great to have and use, and one reason why raw data is not so great to have and use. If you were paying this statistician to do this study for you, and you were interested in this, and they put this on your desk, what's one reason that would make you happy that they put this on your desk? Anthony, go ahead.
I was gonna
Or unhappy. Go the unhappy one. Go ahead.
Because it's just assuming that their employee is going to make that much every week. You don't know.
Oh, that's good. You're being more meta than I wanted you to be. Good. That's making the assumption that next week they do the exact same thing. Let's assume the boss has the idea of a margin of error, and they can put the plus or minus on there. I was thinking way less meta than that. That's very, very true, though. What if this guy had a bad week, right? What if this guy just, whatever, had a really good week?
What if one of them missed a day?
Or one missed a day. Good, good. Let's assume, just for sake of easy comparison, they all work the same amount of time. They're all the same skill level. So apples, for the most part. I love what you're saying. You're being very meta, which is great. And I think you should always be very meta when looking at data. But I'm trying to go way more topical than that. Thank you. Trev, go.
Well, I was going to say the amount of time. You mentioned apples.
Let's go apples. You make everything apples. What's the problem with having a big block of numbers like this thrown in front of you? Think less meta. Think more topical. What do you think, Robin?
I would like to have a definition of what they meant.
Oh, good for you. Good for you. What is a product?
Yeah.
Like define a product. Make sure, whatever it is, whatever they're making, it's the same for all of them. You guys are being very meta. I love this. I do love this. I'm just looking for a more. Hey, what's the who's the slacker this week?
Names and guys.
Who's the slacker this week? But based on, let's define slacker. I like this whole idea of a definition, Robin. Slacker is someone who makes the least amount of products. Who's the slacker? 10. Was it immediately obvious when the data was dropped in front of you? Who's the overachiever?
39.
Okay, good. Now, how would this be easy?
35, actually.
35?
Yeah.
We got 39.
39, yeah.
But you see the problem right there? Is it 35? Is it 39? Your eyes are going all around scanning, looking for this. So you're seeing the problem with having a bunch of raw data dropped onto you? Go ahead, Jennifer.
It's hard to read.
It's kind of hard to read. It's kind of hard to process. To look for the smallest one. We got lucky the smallest one's over here. But that's just because when I hit F9 on Excel, it put the smallest one there. It could be over here somewhere. Suppose you had hundreds of data points in a block like this. You don't want to be sorting through all that. Haley, go. You want some kind of a graph or some kind of an organized method. Thank you, my friend. Now, why is this good? Actually, hold the answer to that question. Here. We want something along these lines. Here's the raw data down here. Here's the raw data down here. This is what I like to call a distribution or a frequency distribution. Okay? This is an organized way of putting the data into a t-table or an XY chart. Think of like an XY chart from back in the day, your algebra classes. X and Y, data and frequency counts. See if you can make peace with what that is showing you by looking at the raw data and comparing it to the data up here.
So it's more clear.
What is, for example, does that 5 mean right there? There's a 5 in the frequency count for 16 to 18. Elena, go ahead, my friend.
So 5 people actually did the same, 16 and 19 to 18, and 5 to from 19 to 21.
Good. So 5 people made between 16 and 18 products. And you can find them down here. There's one. There's one. There's one. There's one. And that one right there. There's your 5 between 16 and 18. Or we could do the same thing for all of them. There's a 0 from 31 to 33. Because there are none. I'm going to stop looking for it because it's not there. Now, why, Jennifer? Your point earlier was fantastic in that the smalls and the highs were hard to see. Are they easier to see now?
Yeah.
They are. One person made between 10 and 12. One person made between 37 and 39. However, what gets lost?
The actual.
The average.
That you lose the actual. You won't have this and this. You'll either have this or you'll have this. The problem with having this is that you lose the actual data values. I want to address that issue on Monday with you guys because the idea is, because of something called the law of large numbers, you don't actually lose that much accuracy. That's what's kind of cool about it. You don't actually lose that much. You do lose something. So for example, 5 are between 16 and 18. So it went 16, 16, 17, 18, 18. That actually balanced perfectly. I was looking for something that didn't balance perfectly. Jennifer!
Well, when you look at the top chart, you see that the 10 is not as bad as it looks there.
Because it's 10 through 12.
Yeah, well, yeah, but if you look at that, like, you see more lower, and then the ones that got higher.
Good for
are
you.
Outliers.
Good for, use that word again. What was that beautiful? Yes,
Yeah,
outliers.
so they look like they did really well, but there's not as many.
So you're saying 10's not an outlier?
Yeah, it's a little bit, but not as much.
Okay, good. We're going to find some ways to quantify that later in this class. I love what you're saying. So 10's not as bad as 39, say, for example, is good. But here's the trick with 39. We don't even know if it's 39. It could be 37, right? And that's the trade-off. That's the trade-off. If you create these distributions like this, and then you frequency them like this, you lose that exactness that's down here. So for example, 37 to 39, we don't know that it's 39. We know down here, it's not up there. So good, I like what you're saying. Although I like what Haley said too about the visual. Because this is cool. This is cool, but it's not as cool, I don't think, in my opinion, as this, which is a pictorial look at it. And Jennifer, the reason I like showing this now is because of what you just said. Those outliers, those unusual values pop a little bit more when you've got this kind of a 2D versus 1D look at it. So you see those zeros that were there? You now see these pop, like, oh, that's kind of cool. And look at this. And then look at this. Like, that really jumps out. This is all gone with the raw data set. Like, those differences, because they're all just placed next to each other in a line, you totally lose all that uniqueness of the distance that 10 is from 39. Go ahead, Elaine.
Yeah, just I wanted to repeat probably because we still don't have exact.
You're exactly correct. All we know is the same 5 people made between 16 and 18, but not how many each of them did. So what we'll do later on, we'll say it now, we'll revisit it on Monday, is I don't know how many products these 5 people made. They made between 16 and 18. Let's just say they all made 17. They all made 20. Mm-hmm. They all made 38. They all made 35. See what I'm doing? I'm just picking the middle value. Mm-hmm. And what happens, and we'll revisit this on Monday, the law of large numbers says that the ones that are below that middle are canceled, if you will, by the ones that are above it. And it's called the law of large numbers because you can't prove it, but it works. And you'll see it again. You'll see it again. I'm going to collect some data at the very end of the day from you guys today. We'll analyze it on Monday, and it shakes out. It's amazing. It's amazing. So, cool? Fair-ish? Believable-ish? Yeah.
Sean, excuse me, can we come back to our birthdays, like because we've got already the whole group?
Oh, for sure. We actually had a huge crew in class on Monday. We didn't get a match. We got close. We were within one day a number of times. We didn't get a perfect match. We'll come back to that for sure. We'll come back.
Birthday?
Matching birth dates. I was looking for a perfect birthday match.
Yeah.
Did we have it that day?
I had October 13th, and then there was another girl that had October 13th.
Oh, I didn't catch that. I didn't really get a much bigger deal about it. I remember like being one day off at a number of places, but then I remember actually getting a perfect match. Well, there we go. I'm happier now. Because it is like, when you have that many people, it's like a 90% chance you're going to have a match. So I'm glad we actually did have one.
Yeah.
But we got so close on so many, I thought the point was proven.
Right.
Even
But that's
among
awesome. I
even
forgot.
among the 4 people last time.
It was still clumping, micro clumps, if you will, micro clumps. So this is a really cool way, and we're gonna use our TIs to generate these a lot. We'll use Excel to generate them too in your projects. Between distributions, now the trade-offs of this versus this, one-dimensional versus two-dimensional. Yeah, this is a much better visual of the data than this is, although this is easier to do mathematics on, which you'll again see on Monday. So again, trade-offs. It's easier to crunch numbers on this, but it's easier to see what's going on in the data set when you see this. For example, half of the data set is between 16 and 20 and 21. It's very easy to see. 2 big spikes right there. The bottom 25% here, the top 25% here. You've got one, or excuse me, the other 50% is here and here. But those 2 large bars are kind of a modal issue, and then this cool bar here gives you almost a second mode that might be happening. So it's nice to have that 2-dimensional look at the 1-dimensional chart up above. Your textbook does a pretty good job in the beginning of overstimulating you with too many types of charts like that one. For example, scatter plots, ogives, I think box and whiskers even show up there. What I want to do is I want to kind of stick with histogram-y types. That last chart called a histogram. That Haley's request was a histogram. So I want to stick with histogrammy type charts for the remainder of today, things that are histogrammy. So the first one is called the Pareto Diagram. We'll explain why momentarily, but what I want you to do first is I want to collect a little data from you guys. So I want you to clear your minds. I'm going to ask you a series of math questions that I want you to answer in your head, but not out loud, but in your head. And then at the very end, I'm going to ask you a non-math question, and I want you to either write down your answer or just keep it in your mind, and then I'll cue you for your responses. Okay, so I'm going to ask you a bunch of little math questions. Just go answer in your mind, and then I'll ask you a non-math question. So, ready? Here we go. 5 plus 1, 2 plus 4, 4 plus 2, 3 plus 3, 1 plus 5, 6 plus 0, 5 plus 1, 2 plus 4, 3 plus 3, 4 plus 2. Think of a vegetable. Think of a vegetable. Screen. So, I guess that'll do. All right. So, let's get some data. What do you think of, Trev? Squash.
Are you serious?
Squash? Are you serious? That was the wrong answer, Trevor. How many squashes do we get? We got 2, right next to each other. 2. It grows very well in Central Oregon, by the way. It grows very well. Zucchini especially.
I
Plant
even
one
don't
zucchini
like
plant.
it. I
One
don't know
zucchini
why
plant,
it
no
was
more.
my mind. I even don't like it.
That's okay. The squash popped in there. What else you guys get? Rob, what'd you think of?
I don't know.
Cucumber.
Cucumber?
I got mushroom.
Cucumber? How many cucumbers do we get? We got 1, 2, 3, 4 cucumbers? Awesome. We got mushroom? Okay. How many mushrooms? Is that a vegetable? Yeah, what the hell? It's called a vegetable. I think cucumber's technically a fruit, but what the hell? Who cares? What else we got?
Carrot.
Carrot. How many carrots did we get? We got any carrots? We got 1, 2, 3 carrots. What else did we get?
I said
Celery.
tomato, but I think that's a fruit.
That is a fruit too. What the hell? We'll put that on there too. So we got tomato. We got 1 tomato.
Potato.
Potato. And we got a celery. Okay, do we get everybody? We may have got everybody. Say again. Spinach.
Eggplant.
Eggplant. 2 eggplants.
I had artichoke.
Artichoke. So what's happening? What's happening is you're getting a clump around cucumber and carrot. I mean, think about it. There's only 15 people or so in the room, and half of you picked cucumber and carrot, and the other folks kind of tailed off with squash and artichoke. The reason, and that's okay. This always happens. Although it's interesting. Now, part of this is probably because the class is so small. Usually, carrot gets a huge spike, and chances are, if we had a larger class, it would get the huge spike that I'm used to seeing. We'll see it in a later class today. But the reason why I like using this data set for a Pareto chart is what a Pareto chart actually does. It's like a histogram in that you've got a vertical and a horizontal. But the horizontal generally has qualitative data on it, not quantitative. So that histogram we saw earlier, number of products was on the horizontal. This is going to be like whatever vegetable you say. And the reason we're going to call it Pareto, or what makes it technically Pareto, is by placing the items in decreasing frequency order. So cucumber goes first, followed by carrot, followed by, I think we had squash, right? Followed by everything else. Mushroom, celery, tomato, potato, and everything else. Not to dismiss everybody else's spinach and everything like that. Spinach also grows very well in Central Oregon. Very, very well. So, and then you scale it appropriately. The largest number we got was 4, so I'll put frequency up here. Put frequency here, we'll put a 5 here. And then we've got a 1, 2, 3, 4. And then we just draw some bars. Cucumbers at 4. Carrots at 3. Some folks will claim the bars have to touch. That's totally fine if you don't want to touch. I don't really have a fit if they don't. Squash is 2, especially for qualitative data. It doesn't really matter. And everything else is 1. And what you end up having is you have basically an exponential looking curve. That's what makes it, the reason it's called a Pareto diagram is because Vilfredo Pareto was the Italian that developed this idea, said years and years and years ago that it was called the 80-20 principle. He said 80% of the wealth is held by 20% of the people. So a disproportionate level of wealth distribution, which I think is probably even more exaggerated today than it was in 18th century Italy or whenever he was around. So the idea it's attributed to him is that you have this beautiful exponential where most of the data is on one side and then it tails off to the other side. And now it's qualitative data, so you can arrange it any way you want it to. But when you arrange it in this way, it's called a Pareto chart. Very often, too, there's another line added to Pareto charts, which is kind of cool, although I don't really fixate on it, where you have the cumulative frequencies stretching off with a line that eventually gets to 100% once all data points are accounted for. And that's great. That's all fine. We'll talk more about that when we talk about ogives. This is really kind of what I like to see, which is the actual exponential kind of decay as it goes away. So that's a Pareto chart. Histogram-y, but for qualitative data instead of quantitative data. Coolish? Yeah, good. All right, let's generate a couple more before I break the screen. Okay, we're good. Let's revisit the screen. Okay, so Pareto chart. Here's 3 letters. Finger, refused, slaughtered. Okay. What is the average number of letters for those 3 words? What is the average number of letters for those 3 words? And I know we haven't talked about averages, but I think we've been taking averages long enough, I'm guessing, from previous. So, 8. I vote for 8. Good. We got some agreement in there. Letters. Hang on one second. I want to write an idea down. Okay, and how did you guys do that? Excellent. We're gonna Uber analyze. We're gonna meta analyze what an average is starting on Monday. But yeah, you got 6 letters there. You got 7 letters here. It's 13 letters plus 11. 24 letters divided by 3 is 8. Okay, perfect. I'm going to show you these words and a few more on the next slide. I'm going to give you 10 seconds to approximate the average length of all the words on that slide. And when you give me what you think you won't have time to actually do like you just did for these, because there's too many words to do. But I want you to give me your best guess estimate as to what it is. And give me something point something. Like 8.0, this would be 8.0. So give me something and then point and then something else. So 1 decimal place of accuracy. Cool? Here we go. Don't waste time laughing. Okay. Did you recognize it? You may have recognized the text from the just had its 25th anniversary. Movie just had its 25th anniversary. There's a great picture of the Princess Bride. Who hasn't seen The Princess Bride? I am envious of you. It's the greatest movie ever made. And you haven't seen it yet, which means you get to go see it for the first time. Very envious of you. Now, it's a wonderful soliloquy from Inigo Montoya. You'll kill my brother, prepare to die. That's just great. Just go buy it. Buy it now. Anyway, it's the soliloquy he gives describing the 6-fingered man, what he did to his father. Point fact is that you couldn't possibly have added up all those words and divided. I think there's 100 or so words in that, or 150 or something. Not enough. So basically, you did your first bit of inferential statistics right there by being able to look at that and say, okay, let's just kind of eyeball this and eyeball. So good. Let's figure out how you did. So what I'm going to do is I'm going to swing this to that board. We'll see if this works. This might work. Yeah. All right. So let me hear some guesses for average length of words.
6.8.
6. Anybody below 6? Jordan? 5? Anybody below 5? So you got 5 points? Okay, other end, anybody go 8 point something?
I was 7.8.
Anybody above 7.8? So everybody's between 5 and 7. This is perfect. Stem and leaf plot is what we're going to talk about next. The reason you like using stem and leaf plots is when you have a fairly large data set, and not that there's 15 or 16 of you in this room right now, it's not a large data set, but all of your data is clumped between 5 point something and 7 point something, which means we only have 3 discrete stems, 5, 6, and 7. I'm going to make this a horizontal histogram versus a vertical one. It doesn't really matter. I mean, I just seem to like them this way. So these guys right here are going to be called your stems. When you have few stems, you can have as many leaves as you want because it's a very efficient way of collecting data very rapidly. So check this out. Now I go, okay, who said 5? 5 point what?
7.
5.7? Who else? 0.4? Who else?
0.2.
0.2? Who else? 0.1? Those are the 5s? These are called your leaves. These guys over here are called your leaves. And it's a really neat way, if you're out in the field collecting data on measurements, if you're out there doing natural resource management, and you're collecting a bunch of data points that are all within, like a bunch of trees that all have similar diameters, a real quick way of getting data down. Really, really quick way. So this is very efficient. 6 points. Throw us out some 6 points. 6.3, point 4, point 8, 5, 0. What, did I hear 2 8s? Were there 2 8s?
Yeah.
2 8s, thank you. Anybody else? And then on to our 7s. Point
I said 8.
0.8, 7.8, beautiful. Anybody else 7s? That's everybody. That's everybody. Very, very quick, rather than having to rewrite the stem over and over and over again. And you can see with a much larger data set, that would be very advantageous, especially if you have more than just 10 possibilities here. So it just saves you all that. It doesn't make sense. It doesn't make sense if you've got a very disparate data set stem-wise, because then you actually end up writing more than you would otherwise, or the same amount. It doesn't save you any time. Okay? Does this kind of make sense? The one thing you want to think about if you're doing these manually is make sure these are roughly spaced evenly. I got a little bit lazy here and I started getting a little bit too big in this bar. These should be a little bit closer. But you want it to look like a histogram. I mean, if you turn your head sideways, you can kind of see the histogram, can't you? Mm-hmm. Ah, it's right about here. Yep, there's your histogram. Kind of bell-shaped. Actual average number of letters per word in that speech? Right about 4. Right about 4. Take a look at it again.
Because some of them was really...
You just discovered your first biased sample. You guys did a biased sample. And I preloaded it intentionally. I preloaded with words like refused, finger, slaughter, big long words.
And you were talking about 6s the whole time.
Oh my God, I didn't even think about that, Anthony. I kept saying 6, 5 plus 1, 4 plus 3, and then here you guys, no, I never thought about that. Maybe that's preloaded, the 6 is preloaded in there.
Bias.
Holy crap. I never thought about that. That's excellent. I used to do this one. Unintentional bias. When I did this experiment before, earlier in the class, talking about a random sample, I used to ask, how many people like broccoli? And people raise their hands, and I say, how do you know? And then we talk about a sample. You haven't eaten all the broccoli in the world. You've eaten some broccoli. And then I would get a buttload of broccoli responses, not realizing that I was front-loading the response by saying it an hour before. But then what's interesting is, broccoli and carrot often come in a 1-2 tie, even without saying that earlier on now. So I can't say anything before I do the experiment. I think that's what we just learned today. You walk in, sit down, shut up. 1 plus 5. Fantastic. No, I think, and taking all that out, there's a lot of bias that exists in here by the size of the words. Think about how many little 1-letter words, 2-letter words there are in this. Tons of I's, tons of it's, tons of he's. But your eyes, E-Y-E-S, are not drawn to those. They're drawn to the big words. Fencing, enough, failed, fingered, slash, demanded. So automatically you're like, oh, 6. So again, that's a biased sample because your eyes are biased against the small words. It makes perfect sense. Can we make this a more random sample? If we had time in more than 10 seconds? Absolutely. And you'll do it in 244. One of the first things I have you guys do in 244 is actually analyze this in a more random way. And you'll play with it then. Cool? All right, let's come back out to here. Yeah. So anyway, stem and leaf, that's beautiful. That's absolutely beautiful. One last histogrammy type. Because these are all the histogrammy types that I think are worth talking about right now. There are plenty more histogrammy types, non-histogrammy types. But these are the histogrammy, and since we're talking about collecting data and then showing it two-dimensionally, and it's called univariate data in that there's only one thing being measured, the average length of a word, the average, or the vegetable that you say, the number, whoa, God, knew that was going to happen eventually. The number of products made by a worker in the plant we're talking about earlier. Let's go here, there we go. All right. Not saying the battery's on its way out, yet it's plugged in. That's interesting. Oh, okay. Must be a Microsoft product. Unplugging and plugging back in fixes the problem. So this is the last one. And I've got one more question to ask you to collect some data. Clear your minds. No broccoli. No Inigo Montoya. No six-fingered man. I just want you, very simple, very simple. I just want you to write down a whole number from 1 to 4. Thing has like a governor on it. All right. This is related to a stem and leaf, but it's even quicker and easier to deal with if you have few stems, but basically no leaves. So pretty much, I just gave you very simple directions. Right? Write down a whole number from 1 to 4. So what are the possible results? 1, 2, 3, and 4. 1, 2, 3, and 4. There's only 4 possible results for this experiment. With a stem and leaf, technically speaking, there are infinitely many, depending on what you guys guessed. And the more precise you get those responses, give me to the nearest 100th place, nearest 1000th place, they can get even exponentially greater. Here's 4 responses. How many of you wrote down 1? Who wrote down 1? Nobody wrote down 1. 2. 2. 1, 2, 3, 4, 5. Very quick. Very quick. 3. Who wrote down 3? Yes, yes. Very often this happens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which I believe is everyone except maybe Trev. Did you say 4?
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have a 4. Any other 4s? We got 2 4s. 2 4s. There we go. This always happens. Always happens. Get a spike at 3. Why do we get a spike at 3? Always get a spike at 3. Why do I get a spike at 3? You're right-handed. Help me out with that one. I am not left-handed. You wouldn't even know that movie because you haven't seen it yet.
No, it's the same philosophy when you shop. They put things at eye level on the right-hand side, so if you're thinking of a linear line 1 through 4, you'd go to the right.
But why not 4 then? Which is all the way to the right.
Too far right.
That's too far. Great, define too far. This is great. I love this discussion. Define too far. Past here, Jen says. Good. Good. It's out here somewhere.
I don't know. It's psychological reason why.
I agree. It's psychological. David, here's my theory. Here's my theory. Think about the question or the statement I said. Write down a whole number from 1 to 4. I didn't say 3, and somehow our brain goes, wait a minute! I must therefore complete that statement by putting 3 down. I don't know. It's a guess.
Well,
Haley's not buying it.
no, I am. Because you said that, like, I wrote down 2, but in my head I said 3.
Interesting. Your brain went 3 even though your hand went 2.
Yeah.
That's kind of a cool disjointedness, actually. That's female multitasking. Guys can't do that. You see what happens? I fell over the damn stand trying to walk. Yes, Jada, right?
I kind of did the opposite because like in these little tests, I kind of just like subconsciously like want to cheat just to like throw it off.
Oh, interesting.
So my head went 2, and I was like, okay, I'll write 2, even though I wanted to pick 3.
You wanted to pick 3, but you wrote down 2.
I thought that everyone would pick 2 because 2's in the middle.
Interesting. I wonder how much of that influences on a daily basis. It's called, it's got a name in statistical sampling. It's like wanting to make the interviewer happy with your answer, as opposed to being honest. Interesting. Interesting. Very interesting. Or smashing the system. Mimi, what do you got?
It might also be because a lot of people picked 2 and 3. It's because those are the 2 numbers you didn't say.
Well, I kind of did. I didn't say the number 2, but I said the word 2. But I see what you're saying. I said 1 and 4, and maybe the discrepancy between the number of 2s and the number of 3s is due to the fact that what you just said. Like otherwise they might be equally spaced. But there's probably still something into the fact that hearing the word 222 has all those different spellings. I like that. That's good. Please, tell me your name one more time. Liz, thank you.
I just like the number 3.
Well, good.
It's a magic number.
Well, good. The problem with it is I can't like write down a number from 7 to 11 because 2's not in. Well, 2's not in there. So I go like 1 to 5. I could try that next time. We'll do 1 to 5 next time. And I always forget this, but when I do the vegetable one, I always want to mix up the sums. Instead of adding to 6, you're adding to something else. But then I start it, and halfway through I realize that I should have done 7 or 8 or 4 or something else along those lines. So Pareto. Oh yeah, Elena, go ahead.
I've just taken speech class.
Yes?
And our speech teacher, she said that people remember, so 3 is like kind of magic number because we remember more if something was said at least 3 times. We think 3.
Interesting.
We think 3. 3 words, 3 something rules.
I would love to see the study that was done to
I
prove
don't know,
that.
but
I would love to
that's-
see it. Well, I mean, repetition is this is why when I designed your guys' quizzes and lessons, they go like this. They're always coming back to square one. Even if I'm not directly assessing you, go, I agree with that. It's just a number. It's interesting, the number 3. I want to go like 13 if it's okay with you, just because I tend to repeat myself an awful lot, more than 3 times. I like it though, I agree. That's why I like this idea too. Put the lesson out there so that you can watch it again if you need to pick up on something. Like he
3
said
times.
something about stem and leaf. Don't watch it 3 times, my God, that's too much Sean to deal with. Jordan, what do you got?
It's talking about remembering and the rule of 3. If you hear something or see something 3 times, then it will stick with you.
Sure, totally. I'm not doubting it. I just want to see how they were able to discover to 3 and not 4 or 2. It's interesting. It's very interesting to me. A repetition, I'm a huge fan. I mean, that's, again, how I set my classes up. So, awesome. So that's all the histogram-y stuff I want to talk about. But what I want to do is just share with you some really rad, and this is all visual stuff, not really to write down. So check this out. Check this out. See if you can get anything from this statistical display. And you may have to move a little closer to see what this says here. Forgive the camera in the middle of it for ruining it.
Where's the green dot? Or green?
Well, the green is actually this. The colors are a little
Oh,
skewed.
okay.
There's the actual colors there of it. Yeah. No, the colors are they look much better on the original.
No, I like the
Yeah.
idea.
So the big green,
You pay attention to the
because it pops. The color pops a lot more. Yeah, it's a lot. Yeah, and that green is nowhere near as dark as that green. So can you guys read the legend? Green is people who live with fewer than $10 a month. Yellow, fewer than $100 a month. Blue, less than 1,000. White, live with more than $100,000 a month. Could you recognize the flag?
Brazil.
Good, exactly. Now, it's not quite Brazil. Brazil also has a banner that comes across the middle of it with a Portuguese saying, which I think says something like, our team rocks at soccer or something along those lines. But what was amazing about this is, when I first saw it, like, oh, it's a Brazilian flag. I'm like, kinda, just in the banner. And then I looked at it more closely. I looked at that legend, and it was kind of like a slap in the face. Because it shows in a beautiful way the disparity that a Pareto diagram could have done just fine-ish. I mean, technically speaking, a histogram in Pareto form. But this does it in such a way to really emphasize the wealth disparity. And I know it's incomplete. Like, how about from 1,000 to 100,000? Where are those people? Well, I don't know. I don't know where they are, but I think the point is made with what we've got up here. I mean, and what was interesting is these folks that did this study actually went in and found these statistics, or these parameters, if you will, parametric values, within the country, and then figured out the areas of the flag that matched up to it, which is really quite interesting. Really quite interesting. Here's another one. Yeah. I mean, the numbers, what would you approximate? What % of that flag is red? Approximately. 90. First thing I think of too, 90. So 1 in 10 14-year-olds in China is studying, the other 9 are working. Now, this assumes that you can't do both, right? I mean, this assumes that a working 14-year-old cannot be a studying 14-year-old. That might or might not be true. That's how it's being portrayed here discreetly. So, this is one of my favorites. It's a bit dated, but then at the same time, it's a bit current. It's one of my favorites. One of my favorites. One of my faves. One of my faves. One of my faves. Yeah. And amazingly enough, this is pretty much what Gallup is saying right now. When they say 53% of their sample with a plus or minus 4% margin of error, which is what the Gallup Poll is saying right now, that essentially says that America is split. Still, 10 years later, it still looks just like this. Maybe not the blue. Maybe a few more Americans know where Iraq is now. We'll test that in 244. So I love this. Non-standard displays of data. It's fantastic. This one's kind of hard. Let's skip it. I'll have it posted for you later. You can check it out if you want to. It's really hard to read. I didn't think about that black background in a darkened room. So this one's a neat one though. I like this one. I do like this one. Technical or vomit-ish, but see if you can figure out what's going on with this one. I like the ones that make you work for it. This is perfect. You got this here.
I love that.
That's me too. I'm gonna save it here for you.
All right.
What's going on with this one? What do you think? Give me some ideas what you think's going on. I'll give you a hint. I just watched Life of Pi flying back from the East Coast on an airplane. Have you guys seen Life of Pi? The movie Life of Pi? It was. Did you read the book too, Jennifer? I mean, the book is my favorite book of all time. I read it 15 years ago. And I remember saying to myself, please don't make a movie out of this because you'll ruin it. And then Ang Lee goes and makes a masterpiece.
I felt that way about the host.
About
The host.
the host, same way. Yeah, I mean, just a masterpiece.
It's like a very hard book to like put
Mhm.
into a movie.
And yet it worked. It worked beautifully the way Ang Lee did it. But this is not Life of Pi, but it's related to it. If you've never read Life of Pi, part of Life of Pi is about a shipwreck, which is what this is about. And this is the Titanic. It just had its 100th anniversary. This is the result of what happened on the Titanic with a couple different parameters. You've got the class of the people on board up top. So you got crew class, first class, second class, and third class. Now, what you don't have are raw data, but you have rough percentages. So what would you say? What percent of the boat was crew? Ish. Ish. Go with ish.
75.
Oh, wait.
Crew.
Oh.
So this is 100%.
Yeah.
So what do you think crew is? Ish. 40, 35, 40, somewhere there, I heard? I'll buy. Okay, so
No,
this...
I get it now.
Oh, you get it now. Okay.
Yeah, I was-
Yes, this one makes you work for it. This one definitely makes you work to understand what the hell it's trying to show you. So basically, there's 100% of the passengers on the boat.
Right.
Roughly that length over that length is the percentage of crew. So you've got what? You've got 40?
Yeah.
How about first? 15? Second? 15? So we got 15. 15 is 30. 40 is 70. So call that 30?
Yeah.
There we go. There we go. That's not bad. That's ish. That's ish, right? Beautiful. So of the crew now, this is why I totally dig this. Break it down by sex.
They're all male.
They're almost all male, aren't they? Look at this. There's a little sliver of pink out here that goes down to the females. But the vast 98, 97, 98% of the crew were male. And then, if we go one step further, what happened to those crew members? So here are the female crew members. Looks like about 2 to 1 or 3 to 1 lived. They survived. So maybe 3 out of every 4 survived. How about the guy crew members?
10.
Right? Maybe 10%, 10% lived, 90% of those guys died. The 10% that lived were probably in the lifeboats, taking people away from the boat as it sank. So it's a neat way of looking at that. Now let's compare the classes. Let's compare the classes. First class.
First class.
Gender?
All survived.
But how about gender first?
Um,
Gender's pretty much, what do you think?
almost the same, but
Right. It's like 50-50-ish. Maybe it's a little bit thicker here, right?
Yeah.
So maybe 60-40,
Yeah.
55-45, somewhere in that neighborhood. Good. How about the first class women? What happened to them?
Like
Most survived.
except like one.
There's Miss Strauss. Remember the story of the old couple? I think it was the Strausses, Ida and her husband. And James Cameron had a field day in the movie with it, showing them on the bed snuggling as the water rushed into their cabin. That's her. There she is. not to make a mockery of it. It was actually quite sweet. He did a great job with it. First class men. Here they are. What happened to those guys?
They died.
Most of them died. Looks like a 3 to 1, maybe. Maybe 75% of them died. Okay. The second class?
More men.
Second class, right? More men than women. And almost the same outcomes as far as survival. It's like more guys survived in second class than in first class as a percentage. As a percentage, right? This bar is a little thicker than this bar.
Yeah.
And here's something else Cameron had a field day with. Look at third class. Here are the girls. And there are the guys. Let's come to the girls first. Here are the girls. The only percentage where women died at a higher rate than the men. Women died at a higher rate than women lived. According to class. A higher percentage of third class women died than men. Men, it looks like maybe, 90-10, 80-20, somewhere in there. And Cameron had a field day with that. Because so many third class people died. And then the discrepancy, and he had a field day saying they were locked in the bottom. I mean, I guess you saw the movie years and years ago. They were locked in the bottom. They couldn't get out because they were evacuating first and second class first. But I love this. It is confusing as hell when you first look at it. But then you get into it and you're like, oh, I actually got something from that. It's better than just numbers because you get these thicknesses of the bars that let you know what's going on. Please, Anthony.
What would you call that?
I have no idea.
Oh.
There's a special software that's used to create this. I have no, I downloaded it, and the problem is you have to have a very specific kind of data set with full of conditional probabilities and conditional outcomes, and I forget the name of the software. If you do Titanic graph, a Google search for it, and do an image search, it'll pop up, and you can track it down. I don't know what to call it, other than making you work for it graph.
Do people actually use it?
It's kind of a kitschy thing. What I'm showing you here is not for like scientific purposes.
Right.
It's just kind of getting your attention kind of stuff. Like this one. I love this one. Well, that's $100 bill. Okay. So here's $100 bills, aka $10,000. Okay? So here is a 6-foot tall dude for reference, and $1 million in $100 bills. That's how big it would be. That's how big it would be. Okay? So like there's $1 million. Yay. Okay? That's a bunch of those packs on a pallet, and that's $100 million. Would fit on a pallet because you need a forklift at this point to move it around. So let's make $1 billion. Let's make $1 billion, which would be what? 10 of those. 10 of those, right? That's $1 billion. So check this out, friends. That's $1 million. Okay? That's $1 billion. Okay, what's coming next? Right, these numbers are getting thrown around a lot these days. Million, billion, trillion. I've actually heard a politician once say, I don't care how much money it takes. $1 million, $1 billion, $1 trillion. Really? You don't care if it takes $1 trillion? Because that's what $1 trillion looks like. And please notice the guy over there. And please notice that they're too high. So I care if you spend $1 trillion on something versus spending $1 billion versus spending $1 million. And I also care that that's our national debt. As of 2009. So add a few more levels onto that since 2009. That's disgusting. He's still over there. Hi. There he is. Hi. Hi, there he is. Getting threatened by immersion by... Robin!
Didn't you say, or didn't you show a sentence yesterday that said after you're done reading it, then it'll grow like
Yeah.
$100,000 every 6 seconds. Yeah, I wonder if that rate's still the same or arguably the same.
I know there is a website that you can go to that I saw
Tracking the debt.
Yeah, in government class.
Yes.
But, like, it just keeps moving.
I
and
know.
moving and moving.
I know. It's, yeah. I mean, you have to spend money. I totally get it. You have to spend money. You also have to question where the money's going, which is where we come as informed citizens. I like to close with this one. This is one of my favorites. And it's also very depressing, but it's also one of my favorites. So you may have seen this before.
Yeah.
You may have seen this image before. But as you look at it, you're like, it's kind of like a crappy copy. It's all pixelated. Like they made a JPEG and then blew it up too big. So I want you to focus just on that spot of it for a second. Let me zoom in on just that spot. And it's even worse now because I zoomed in. So let's just look at those, like the teeth on the skull there. And you start zooming in again. And you're like, oh, wait a minute. Now the pixels are getting really big. Let's zoom in on that. And what you notice is all those pixels are actually little tiny cigarette box tops. Here's the part that's going to make you catch your breath. I checked this again today just to see if the number still holds. It basically does. The number I read was 400,000 are going to suffer some kind of health-related problem directly attributed to cigarette smoking. Chris Jordan is a genius. He's a Seattle-based artist. Here's the original, Van Gogh, skull with cigarette. That's Chris Jordan's copy of it. He does this all the time. He calls it Portraits of American Consumption. I've given you the link here to his site. I've also got a link off the original page. I encourage you to check it out. His work is phenomenal, and it's depressing as hell, but it's phenomenal. And if it does nothing than raise your attention to it, that's kind of what he's after. It's kind of what he's after, is raising your attention to what's going on. So these are not traditional ways of presenting data at all, not even close. But my God, right? Holy crap. When you see that and you realize what you're looking at, very often at his shows, you'll see people kind of like in real close to him. There's one of his great one. There's 5 big orange rectangles. And these rectangles are the size of these chalkboards, or whiteboards, I guess. And there's a picture of 2 people. Turns out there's parents squinted down looking at them. They're tiny little prison outfits, prison uniforms, little orange prison uniforms stacked. And it represents the number of incarcerated Americans at a certain point in time in 2011 or something. And it's staggering. You look at it, you're like, holy crap, how many is that? And then on the plaque it tells you, just like this tells you. And it just makes you kind of like shake your head and holy crap, holy crap. And hopefully at some point motivate someone to do something, to change something. But that's the thing, it all starts from little things like this, potentially. So that's kind of the if you will, non-standard graphs. I'm not holding you responsible for those. Those are just like, hey, this is cool, you should check this out. The histogrammy stuff is what I want you to kind of focus on right now, and we'll focus on it in class as well. But I do have one more thing to ask you guys. I want to collect a little bit more data. How many keys do you guys have on your person? Does anybody have no keys at all with them today? Anybody have no keys at all?
Just keys or like
Yeah,
other
that's
things
what
on
I'm
it?
saying.
'Cause like I.
Let's define a key. This is a good question. This is a good question. So if you have like a fobby thing, like a magnet that opens a door, you can call that.
Okay.
So call your little car clicker thing, call that a key if you want to. Yeah. So if you have like a push button opener for your car, call that a key. If you've got a fob they use to open doors on campus, call that a key. This is all good. I think I stopped recording now. Now we can all do it in a minute. So anybody have no keys at all? No keys, okay. Anybody have one key, exactly one key with them today? We got 1, 2. 2 keys, exactly 2 keys with them. We got 1, exactly 2. Whoa, wait, count, fine, count. 3 keys, just 3 keys. 1, 2, 3, 4. 4 keys. 4 keys. 1, 2, 3. This is perfect. We'll put this data on Monday. 5 keys. 6 keys. Whoa, 7. Do I have everybody? Anybody have more than that? Oh, what do you guys have?
I have 17.
17!
Oh my God.
17! 12! I was worried about not having an interesting data set. 8! 11! Oh, this data set just got that much better. I got everybody now? Yeah, that's okay. We got everybody now? This is fan-freaking-tastic. That's going to be an awesome data set. I can't wait to analyze with you guys on Monday. That's got so much to talk about. Great. So, here's the deal. We're done for the day. So, as far as like how homework works. So you see this popped up here? Homework for Intro to Prob and Stat. So what you'll do, let's go through it together. Let's go through it together. So, because as Elena said, the website is full of a lot of information. Let's make sure we can find what we need to find. So later on today, I will update the schedule page. We'll go to it right now though. Yes, plug and check. We're going to wait for the computer to load. There we go. COCC. Okay, so we'll go to my website at the S rule suffix. Okay? Hello. Go to your schedule page. Later on today, I will update, you guys are here, I'll update this with the PowerPoint from today, and as soon as I get the YouTube link, I'll put that on there too. So you'll have more stuff there to look at. Homework sheets right here though. And I'll also put a link to this homework assignment in this cell down here as well, just until we get used to going back to that sheet. We'll train you guys into it. Okay. So you go to that homework sheet. Boop. Here's your homework for Intro to Prob and Stat. Click on that bad boy. It opens up to another sheet. Here's some stuff from your book. And then you've got these E problems underneath, and the E problems underneath are the ones I've kind of found in the world. It's not example, it's just extra. It's extra that I couldn't get into the actual book itself because it's not a custom publish. So these are just E for extra problems. So these are the book problems up here in the blocks. Here's are the extra problems down here below. And just have at them, bring your questions on them on Monday. We'll start the day Monday by answering those questions, and then we'll move on to analyzing your awesome key data.
And they're graded.
No, you keep those.
Okay.
The quiz next week is going to have content like this on it.
So it's like do it kind of for help.
Basically do it so we can have a meaningful discussion about it in class, kind of a thing, right? And then you take it home and think about it some more. If I take it away from you right then you can't think about it anymore until I give it back to you.
So bring it just so we
Bring it done and make sure that you've got any questions, we get them answered.
Okay.
Cool, make sense?
Yeah.
Awesome. You guys have a great weekend. We'll see you in a few days. Rock on. I'll get this thing posted.
So it's like if you